Hello, this is Mr. Collier, and today we're doing binomial distribution. Alright, so let's get into it. First of all, we're going to do some of these. It's kind of related. But for C2, or as I like to do it, for choose 2, now you can get it on your calculator, but non-calculator, we have the formula from the formula booklet. It's going to be 4 factorial over 2 factorial, 4 minus 2 factorial, which is 4 times 3 times 2 times 1 over 2 times 2, right? So it's actually just 6, right? You can also get it from Pascal's triangle. If you go down to the 4th row, 4 choose 2 is the second entry. This is 0, 1, 2, 3, 4. 4 choose 2 is this one right here. Which, yeah, you can use this for smaller values like the next one here. 5, 10, 10, 5, 1. 5 choose 3 is the 5th row, and the 3rd one, 0, 1, 2, 3. So that equals 10. We can keep going, but we can also use the formula. Let me demonstrate the formula again. Okay, that's 6 times 5 times 4 times 3 times 2 times 1. And, well, 6 factorial is, 3 factorial is 6, so that cancels with that. We've got another 3 factorial. Okay, so this is just 20. Now n choose 1, well, that's n factorial over 1 factorial, n minus 1 factorial. But n factorial divided by n minus 1 factorial, well, the n minus 1 factorials cancel. It's just n. Okay. N choose 2, similarly. This comes up a lot. You're often asked to solve equations involving this kind of stuff. So that's n times n minus 1 times n minus 2 and so on. That's 2 down here. And this is n minus 2 factorial, which cancels, so you get n squared minus n over 2. Okay, anyway, moving on, let's look at some actual binomial probabilities. Consider a situation in which there are 2 possible outcomes to a trial. Okay. Consider bias coin for its probability of heads is 2/3. Okay, and of course that means tails is 1/3. I'm just going to call it not heads. Okay, the reason it's called binomial distribution is, bi means 2, so there's 2 possibilities, success or failure, one or the other. And whenever you have that kind of situation and repeated trials, it follows a binomial distribution. As long as the probability remains constant, and as long as each event is independent of the previous ones. And we'll talk about that in a second. Okay, a coin is tossed 4 times. What's the probability of 2 heads? By listing all the ways it can be done. Okay, let's list all the probability. Let's see, 2 heads. So heads, heads, tails, tails. Heads, now I can just take this head and kind of rotate it over this way. Or the first one could be tails, and then you get heads, heads, tails, tails, heads, tails, heads. And then you have tails, tails, heads, heads. That's all the ones starting with tails, and then you could have, let me see, or is that it? Is it just 6 of them? I think it's only 6. There's the only 6 ways you could do it. Okay, this is related to something we just did. You can think of this as what we just did, the procedure of listing it. You could have done it with combinatorics. You could think of it as 4 different trials. And you could think of it as there's 4 blanks here, and there's 4 choose 2 ways to place the 2 heads. Okay, and 4 choose 2 is 6. We just did that one above, right? And we listed 6 outcomes. Okay, so 4 choose 2. There's 6 different ways this can happen. So now if we want to work at the probability of 2 heads, we can do 6 times each of these probabilities, right? Or well, actually all these probabilities are the same because it's 2 heads, 2 tails. The probability of heads is 2/3. Okay, and there's 2 heads in our list, so the probability of getting 2 heads is 2/3 times 2/3. And the probability of not having heads, or in other words tails, and there's 2 of them, we get this, right? So yeah, because it's all the same. Like if I did this probability down here, this will be 1/3 times 2/3 times 1/3 times 2/3. It's the same thing as this, right? And there's 6 possibilities here in blue, so that's where the 6 comes from. Okay, so if we work that out, you should get 0.296, or about 29.6%. Alright, let's look at another example. Find the probability of getting 4 heads from 5 tosses. So again, we got like 5 possibilities, 4 heads. Well, there's 5 choose 4 ways to choose. Let's do it over here. There's 5 choose 4 ways to select the blanks for the heads. Okay, and then there's 4 heads. So that's 2/3 to the power of 4. And then there's 1 tails, so that's 1/3. Okay, and you do all that, and you get 0.329, or 32.9%. Alright, so you can see it's kind of the same pattern all the time, and so that's why there's a formula for it. And we're going to talk about that in a second. So we say a distribution in which a trial has 2 outcomes, normally called success or failure, is repeated n times, where each trial is independent of and identical to the others. Those are the conditions for this kind of probability to work. This is called a binomial distribution. If the probability of success, okay, is p, then we can write the distribution as this. So we say this is the notation. X has a binomial distribution of np. Let's go back to the previous example. In this case, X has a binomial distribution of 5 because there's 5 trials, and the probability of success was 2/3. Okay, this is a shorthand way of saying all that. X has a binomial distribution with 5 trials, and the probability of success is 2/3. So in general, yeah, X has a binomial distribution of that, and the formula is probability X equals X is, well, you get the binomial coefficient here, so that was the number of trials. Choose, I guess you need something like a K or something. Let's call this K. It's not good use. So n choose K times probability of success to the power of K times failure is 1 minus P, okay, to the power of n minus K. Okay, so this is the formula, which is actually not in your formula booklet. We have this function on the calculator. You do not need to know the formula for the IB anymore. So on the HP prime, you can go to click here, probability, and we click on density. You're looking for density if you're looking for a certain probability, and binomial, and then you can always click help to see what you need to type in, but you just type in these things: 5, 2/3, and then, so in this case we're looking for a probability of 4, so then you just type in 4, so you can tell your calculator you're looking for the probability of 4, and you see you get 0.329. Okay, so you need to type in N, P, and then the X or whatever you're looking for. Let's do some more examples. 20% of adults are left-handed. Find the probability in a sample of 8 that 3 are right-handed. So we say x has a binomial distribution of 8 because we're selecting from 8 people, and the probability of left-handed is 0.2. And this question is asking us for a probability of exactly 3 left-handed. So we just type those numbers in your calculator, 8, 0.2, and 3. I'll even copy and paste. So 8, 0.2, and 3. Okay, 0.147. Alright. Probably the 2 are left-handed. Well, that's just sticking 2. Actually, you can also type these things in function. I'll show you that. So you can go to our toolbox, probability, density, binomial, type in 8, comma, 0.2, comma, and I'm going to type in x. I don't think we can graph it, or maybe we'll give you a bar chart. We'll check it in a second. But you can go to num, and actually let me just go to shift num to do some setups and go up by 1. Okay, let's go back there now. So this is the probability of getting 0 left-handed people. And this is probability of 1, 2, 3, 4, 5, 6, 7, all the way up to 8. That's the maximum number of left-handed people. So you can see having 8 left-handed people is very, very unlikely. The most likely thing to happen is that there's 1 left-handed person in a sample of 8. So we call that the mode. All right, maybe I'll write that down just as a side thing. Mode equals 1. Okay. And we'll look at the mean and stuff later. So anyway, we can get all the answers we want. See, this is 0.147, which matches what we got here. And if we're looking at 2 left-handed people, that's 0.294. 0.294, or 29.4% chance. Okay, so next we're going to do the cumulative distribution function. It means cumulative means up to that point. So if we look here at this table, probability of 0 heads is 0.618. Probability of 1 head is 0.336. So of course, if you do the probability of less than or equal to 1 heads, then you can just add those probabilities together. Or if you want to get the probability of less than 4 heads, then you can add up these 4 before it. Okay? So you can do all the probabilities and add them up, but with a cumulative distribution function, it's already added up for you. So we can just use our calculator one step to do that. So probability fewer than 2 is less than 2. This is a discrete random variable, so you can't have numbers in between. So less than 2 means less than or equal to 1. Most calculators handle less than or equal to, not less than. So you need to do that conversion, and it makes sense if you look at the table. You would ignore the 2 and add up the previous couple of probabilities, right? We don't need to use the table though, because like I said, we can use this toolbox, probability, cumulative, binomial, and then just type in your numbers in the distribution again, which were 8, 0.2, and 1, not 2. We have to type in 1. That gives you less than or equal to 1, and that probability is more than 50%. 0.503. More than, so let's look at this one, more than 3. Greater than 3. That is the same as, now greater than 3 means, let's go back to that table. Greater than 3 means 4, 5, 6, 7, 8. So you can just add those together. Or you could do, they all add 100%, right? So you can do 1 minus probability x is less than or equal to 3. Or you could do probability x greater than or equal to 3. Those two probabilities are the same. Traditionally, calculators would only do this thing in red, or actually traditionally you would look up a bunch of tables in the back of a textbook. But I think our HP Prime can do this one here, but I'm going to do the one in red. So we can do, I can do 1 minus probability cumulative, not binomial, cumulative binomial and cumulative binomial, and then we type in the, what is it again, 8, 0.2, comma 3, and yeah, you do 1 minus that, you get 0.0563. Okay, but I think on h prime you can also do it this way. Let's see if it works. Oops. Probability, cumulative, binomial. So you can do, well, I should just copy and paste. I keep typing the same things each time. You can do 3, comma 8. So that goes from 3 to 8. So this works out probability x is greater or equal to 3. And, oh, it doesn't work, does it? I don't think it does work, does it? Yeah, oh, actually, I wanted 4 there. Sorry, that's my mistake. If you want greater than 3, it's probably x is greater or equal to 4. So let's check that out. Yes, so this matches our answer we did the other way. Okay. Okay, next use your calculator to solve this. So, yeah, if the probability equals 4, sorry, the probability of success is 0.2, and the probability of 4 successes equals 0.1107, find n. Alright, we can type that in on our calculator and solve that. Okay, so I can do that here. And, wait, what is that? Okay, density function, binomial. So this time we get to put an x in for the n, and 0.2, and then 4. I meant to do that in the function app. Let me just see if I can copy and paste. Okay, I'm going to paste. Alright, the function's in there, and n is a whole number. Okay, when n is a whole number, it's best to just look at the table and see when it equals 0.1107. So let's go to the table, and we just scroll till we get 0.1107, and you can see it is when n equals 11. Okay, so n equals 11. You can show the table if you want. 0.1107. If you show the table to show your work, you need to show what came before that number. Okay, so n equals 11. Here's p. P is a probability, so it could be any number between 0 and 1. It's not like n, it doesn't have to be a whole number, so we can solve this by graphing. Okay, so let's go and do that. Let's type in the same thing. Actually, I should have just written over that. Alright, so 11, comma x, comma 7, and I can solve 0.0379. We can plot. Okay, you can barely see it, but maybe you could zoom in. I think there's only one solution in these cases, so, or actually there could be more than one. Let's just make sure p equals 0.35. Let me go zoom in so you can see that a bit better. Let's try zoom auto scale. Okay, actually there is 2 solutions. So let's see if they both make sense. Let's get this one over here. Function, intersection. So p equals, then we've got p equals 0.867. Right, 867. Both of those are between 0 and 1, so we have 2 possible answers. Okay. To show your work, you could draw this kind of thing. Alright, 0.0379. Both those answers are valid. Sometimes we get a negative number or a number bigger than 1, so then it's not valid, but in this case we have 2 possible answers. Okay. Next, this one's pretty much the same, so you can try that yourselves. let's take a look at the next one. Okay, if I have the probability of score when taking a penalty is 0.25. How many would I need to take to ensure at least one is greater than 0.9? Probability of scoring at least once. Okay. So let's say X has a binomial distribution. So we don't know that one. N, comma 0.25. And we're looking for a probability X at least once is greater than or equal to 1 equals, or is greater than 0.09, 0.9. And if you want, you could do 1 minus probability X equals 0 is greater than 0.9. So we could do this probability. Okay, so let's type that in to the calculator. Okay, let's clear that. 1 minus toolbox probability density binomial. So we have n we don't know, so let's call it x, comma 0.25, comma 0. Alright, and then we can just look at the table to see when this value is greater than 0.9. So that's when n equals 9. Okay, so n equals 9. We can see that clearly from the table. Table says at 8 it's 0.8998, but at 9 it's 0.925. So the answer is definitely 9. Okay, expectation means the expected value, and then we're going to do variance. So let's look at the formula booklet first. Formula booklet, probability sections over in topic 4. You get these two little formulas here, often very overlooked because they're tiny, but this is how you get the expected value and the variance. Okay, and the expected value kind of totally makes sense intuitively as well. One thing people commonly mistake is they use these formulas for stuff that's not a binomial distribution. Please don't ever do that. Now here this kind of makes sense. Look, you got 100 trials and a 0.7% chance of success, and you do something 100 times, then the expected number of times of success is obviously 0.7 times 100, or 70. That's why the formula in the formula booklet is just NP. Okay, the expected value equals NP, which is N is 100, P is 0.7, so it's obviously 70. Okay, for the variance, we got this formula in the formula booklet. So the variance up here, you always just substitute these values in, right? Yeah, so it's pretty easy to use the formulas. So let's check out this here. It's just dice rolls, I guess. So the expected value when you roll dice is expected number of sixes. Okay, so looking at probability of getting a 6, so you just do NP. So if you roll 12 times, obviously you'd expect to get on average 2 6s. And the variance, you can just use the formula. It's NP, so it's 12 times 1/6. And then 1 minus P is 1/6. And that works out to 5/3 or 1.6 repeating. So very easy formulas to use, but they're often overlooked.